Okay, so welcome to the first network theory reading group of the year. And to start this new year, we welcome Michel Davydov that will speak about Poisson approximations of sums of Bernoulli random variables. Michel, the floor is yours.
Thank you, Fabien. Hello, everyone. So I'll talk. My aim here is to give a talk more about sort of a 1 hour long mini course on Poisson approximations, giving just the main results and applying them to in the simple case of approximating kind of the simplest object possible, which is a sum of Bernoulli random variables. So please don't hesitate to interrupt me at any point. So the goal here is to sort of show how you can take a random object and see if you can sort of replace it with a simpler object, which is a Poisson distribution. So this idea of replacing something something complex by a Poisson distribution is very commonplace, and it takes place in many applications. I just put a few that are kind of interest to me, but there are way more applications than that. But just networks and queuing theory and neuroscience. So just my three fields of contact with these ideas of Poisson approximation. And so why is the Poisson approximation so useful is that it sort of arises naturally as a limit distribution in many situations. Basically, as soon as you have independent rare events, you can sort of approximate them by a Poisson, because this is exactly what Poisson distribution is. In case everyone is not maybe is a bit rusty with it, but it's just you have some okay, it doesn't work if you have some time frame, you have to have some time frame. You take some 0t, for instance. You have some events that happen independently from one another, and the number of events that happens follows a Poisson distribution. And, so if I call n the number of events, the probability that it equals k is equal to exponential minus lambda to the power of k divided by k factorial, where lambda is the mean number of events. Okay, so this is just like a reminder for. And so here we're interested in showing that this Poisson distribution is close, in a sense that I will explain in the next slide, to other distributions which are sums of Bernoulli random variables. And so the idea here is to look at a particular case to showcase different standard methods which can be generalized. And I'll talk maybe a little bit about the generalizations, but I'll mostly focus on the case of Bernoulli random variables, of sums of Bernoulli random variables. So yes, so as I said, the plan of this particular, so our BKs are Bernoulli random variables with parameter PK. We make no additional assumptions at this stage. So we're just BK is equal to 1 with probability PK and equal to 0 otherwise. So probability 1 minus PK. And we're interested in behavior of the random sum with n being fixed. And so n being fixed in different settings. So if we'll look at n fixed in n, and we'll look at the simplest case where the BKs are independent. And this will give us a classical theorem which is known as Lecam's theorem. Then we'll sort of give it one possible generalization. There are many possibles, but one is in the case when n is no longer fixed, but is a random variable. And then you need an additional condition on the BKs. You need them to be conditionally on the value of n. They need to be independent and still follow a Bernoulli law. And finally, the last part of the talk, the second part will be pretty short. The third part of the talk will be to study the more general case where the BKs are not necessarily independent. And I'll present a very classical and very powerful method for Poisson approximation, which is called the Chen-Stein method. So, well, as I was saying, what we want to show Poisson approximation. But in what sense do we mean that we have a Poisson approximation? So what kind, if we were saying approximation, it means that it's kind of close. But so if we were talking about how close distributions are one to another, we need some kind of distance between distribution. And so a natural metric to measure this proximity is the total variation distance. So how do we define the total variation distance? Well, we take the measures and P and Q on the same sample space or omega, and the total variation distance between the two is basically the greatest common mass that you can have between the two, or like this kind of another common mass, the common distribution of mass. So we're looking at the largest A, such that the difference of the two is big. So the closer P and Q are, the more distribution of mass they share, the smaller this supremum is going to be. And so when the sample space is countable, we can show that this definition is equivalent to saying that this is equal to 1/2 over all the sum over all omega of the absolute value of the differences of the kernels of the sample space in some sense. And so in the literature, sometimes there's a constant, this constant 1/2. Sometimes you find it as a 2 over here. Sometimes so just a convention. I'll use this convention in the talk, and normally I didn't make any mistakes about this in what follows, but then the math changes the constants up to a factor 2.
Michel,
and this type of conversion, so yes.
In your equivalent definition, don't you require that no single event probability is greater than 1/2?
No, the distance in total variation is a number between 0 and 2.
Oh, okay. Okay. Maybe I missed that. Okay, thank you.
Okay, yeah, I didn't mention it, but yeah, it's the probability. The distance itself is not a probability number 1 and 2. And so it's total conversion total variation is stronger than just weak conversions, which you can sort of see just from the definition. So now let us go to the first real part of the talk, which is to present what happens in the case where we have a sum of independent Bernoulli random variables with parameters pk. So in this case, there is a result which is called the Lecam's theorem, which I will prove because the techniques involved in proof are very interesting and are susceptible to be easily generalized to more general settings. So I think it's interesting in that sense. So, but what does the theorem state in itself? So what we have is, give me a second to take this. Okay, this doesn't work either. Okay. So what we have is we take the sum of Bernoulli random variables. We call basically lambda. It's the mean of the sum. This is the mean is equal to the sum of the pk's, and we take a Poisson random variable with the same mean as the sum. Okay, this is the same. And then we can bound the total variation distance between the sum of Bernoulli random variables and the Poisson random variable by the sum of the probabilities squared. So in particular, if we have some kind of convergence of the mean, if just the means, if the mean of this converges when n goes to infinity, and if this goes to 0 when n goes to infinity, it's a big N here. Then we have the convergence in total variation of the sum to a limit Poisson distribution of parameter, the limit of the sums. So well, what this theorem says is that you can, in the case of independent random variables, you have a very nice, very clean bound between the sum of the independent Bernoulli variables and the Poisson distribution. So basically, we're sort of conserving the mean. We're saying, well, we have the same mean, and then if the probabilities that we're not equal to 0, so that we're equal to 1, are not too big, then we're pretty close. Okay, So if the pKs, which are the probabilities that the pKs are equal to 1, are pretty small, then the total variation distance is going to be small as well, and the approximation will be good. So this is a key idea for later, is that what matters is the in Poisson approximation in the setting are the probabilities that were not equal to 0. So it actually won't be that useful in what I will be presenting today, but it's the basic idea that allows for many types of generalizations of this result. So before proving this result, I want to introduce like the key ideas behind the method proofs, which because I think they're very beautiful and very interesting, and most of the results that I'll present today, all the proofs that I'll present will be based on what is called the coupling method. So what is the coupling of two random variables? But basically, it's just a random variable on the product space of the two, such as the marginals are equal to the distributions of interest. So why this basically allows sort of to customize the behavior of the couple. You can sort of customize this to fit your needs, whilst conserving the marginals, and so conserving the sort of the distances between the two. And so the key coupling lemma, which is a very easy result, but which is of paramount interest, is that if you have two random variables with the given probability measures, P and Q, the total variation distance between the two is less than the probability that X is different than Y. And so the proof is very short. You basically just write out, you sort of make you just sort of juggle with the probabilities to make the probabilities of X different than Y appear. There are several, so the proof takes about 3 lines. But it's more interesting to see why is that an important result. It means that if you have some coupling XY of X and Y with XY two random variables, which have respectively probability measures P and Q, you can bound the distance between between the distributions P and Q by taking such a coupling that probability of X different than Y is small, because this probability is a probability relating to the law of the couple. So this is a way of bounding the sort of the distributions of the marginals based on the coupling. And actually, this is a slightly more complicated result to show, but you can show that the total variation distance is actually equal to the smallest possible value of the right-hand sign in this inequality, and the smallest on all couplings. So you take all couplings such as the marginals are fixed to P and Q. You look at the probability that X is different than Y, and there's a 2 missing here. Sorry, yeah, it's 2 times this, because it's just the same. It's because of the convention. Sometimes some certain results are true up to a constant. But sorry. Because of the way I defined it previously, here the total variation distance is a number between 0 and 1. I'm sorry. I think, yeah. Okay, sorry, it's just it's easy to get confused with the conventions, but basically, yeah. So you have you can see the total variation distance between the two distributions as the smallest possible probability that the marginals are different, and you take the infimum over all the couplings. And so now we can apply this to prove Lecam's theorem. So the idea here is to find, and which is kind of a common idea for coupling results, is to find a coupling of our two random variables, so of the sum of Bernoulli random variables and of the Poisson random variable, such that the probability that they're different is smaller than the bound we need, which in this case is 2 times the sum of the pk squared. And so one way to do this, we sort of, it's just a way you take a coupling and you sort of verify that this condition takes place. And so here we take the following coupling. We look at the couple. We say we put the following values on on the different values that the coupling can take. And you have to verify that this indeed defines probability distribution, that you have the right marginals, which is relatively easy to see, I think. Here, well, since all the variables are independent, because you can you construct them independently, you can take the sum. So each yk is a Poisson of parameter pk, and you know that if the yks are independent, the sum of the yks will also follow a Poisson law, and the value of the mean of the Poisson law will be the sum of the pk's. And so, of course, by definition, Sn is the sum of the xk's. So now what we have here, we've constructed a coupling, and now we just want to calculate the probability that xk is different from yk based on the coupling we have defined right here. Yeah. So by the coupling lemma, as I said, you can see that the total duration distance between Sn and Ln is by definition less than the probability of the sum of xk's different from the sum of yk's, which is of course less than the sum of one of the terms, the probability that one of the terms is different for some k. And of course, this is less than the sum of all the probabilities of xk different from yk. And this can be computed explicitly because the coupling is very simple. And it's just, you can show that it's just equal to pk times 1 minus exponential of minus pk. And this is smaller than pk squared, because 1 minus exponential minus pk is smaller than pk. And so basically, this works with the coupling we defined here, but you can construct many couplings. And as long as they verify that probability of xk different from yk is equal, for instance, to pk times 1 minus exponential of minus pk, then the proof will work. You can see it's very flexible. And so you have many choices of couplings, and the idea is when you construct the coupling, how do you get the idea of taking these particular values? You want to sort of maximize the values on which the two coincide to make the sort of the mass, the values where the mass on the values where they're not equal as small as possible. And so this concludes the proof. Okay, are there any questions on this first part? Okay, if there are no questions, I'm moving on. So now, so there are many ways of generalize this result. You can actually generalize it to sums of independent random variables which are not necessarily Bernoulli. Then you get a compound Poisson limit distributions, so a Poisson sum of independent random variables. And here I want to present just one generalization which has been of particular use to me, which is a simple version of that, which is the case where you sum a random amount of independent Bernoulli random variables. So you have so here n is no longer an integer. Now it's an integer valued random variable. And in this case, you can show, and the proof will be very easy, that you have a result very similar to Lecam's theorem. As before, what we want is to preserve the mean of the sum. So we take lambda equal to the mean of the sum. Now it's no longer lambda n because, well, the n is random. So you have to, the mean it depends on n itself. And so you take L to be a Poisson distributed random variable with mean lambda. And then you get basically the same bound in the sense that the total variation between the sum of Bernoulli random variables and the Poisson random variable will be less than the expectation of the sum of the pk squared. But this time there's the expectation, there's an expectation because the sum is over of n terms where n is random.
Hello, Michel. Can I ask you a question?
Yes.
What is the distribution of n? Because you say n is a random variable now. what is the distribution of it?
There's no conditions on the distribution. It's just any inter-valued random variable. So it can be Poisson, it can be I don't know, zeta, or whatever you want. It doesn't have to be over all of n. As long as it's inside n, it's fine. All we want, the most important part, the most important condition for this result to work, is that the Bernoulli random variables you consider have to be independent from n. In the sense that if you basically if you condition on the n, so if you take I don't know, the value of Sn conditioned on the fact that n takes the value k, you want this conditional law to so for this conditional law you want the bk's to be independent and be Bernoulli random variables with parameters pk. This will be clear in the proof. So if they're independent from n, you're good. Okay, this answers your question? N is just any, you can imagine n is a Poisson distribution, for instance. This is like the most standard case. So you have, you sample n basically, and then you sample an amount of Bernoulli random variables, which is equal, and the amount is equal to your sample of n, basically.
Okay, thanks.
Okay, is that clear? Okay. So if there are no other questions, moving on. So now we'll prove this, and this will be actually, we won't need any coupling arguments here. We will be able to derive this directly from the standard Lecam theorem. So what we do is that wait, let me just check some. Yeah, okay, I'm good. So we use the formula of total probability since we want to bound P of Sn equals to L minus P of L equals to L. Well, to sample that, we need to know what the value of n is, because if you can imagine that n is fixed, then you sort of go back to the previous case where n was an integer. So if you look at the conditional law, if the n and bk's are independent, well, the conditional law will just be a sum of a fixed amount of Bernoulli random variables. So that's exactly what we do. We take, by the formula of total probability, we condition on the values of n here. And now we can apply the standard Lecam theorem to the conditional law, because if you look at, take the pen, sorry. If you look at this, okay, if you look at this, this is exactly sum of of k. So this is probability that k equals 1 to q of bk is equal to L. So this is exactly SQ, where with q fixed. So so kind of conditioned on n equals q, of course. So the conditioned on n equals q, here you get sum of independent Bernoulli random variables. Here you get a Poisson random variable with mean q. Q times the sum of pk's. And so here you can, by the standard Lecam theorem, you can bound it by the sum of the pk's squared for k from 1 to q. And so here q is fixed because we conditioned on n equals to q, and we're looking at one of the terms in the sum here. Basically, we switched those two, and we're looking at one term of the sum. And so now, well, we can bound the total variation distance by the sum over all q of this. Okay, we replace the distance by the sum of the pk squared, and we're just left with this term. And now what you can see is that here is just by the transfer formula is just the expectation of the sum for k from 1 to n of the pk squared. So this is just an application of the transfer formula. You can see it very easily going from the bottom line to the second line from the bottom. Okay, and so we have proved the result. So in this case, so we can, this is a generalization of the standard Lecam theorem to the case where the number of variables you sample can be random, as long as it's independent from the variables themselves.
Hi, Michel.
Yes, hi.
Could you please remind me if L is dependent on N?
Sorry?
So on the so the probability of L equals to small l condition on N equals to Q. I was wondering if the random variable L depends on the value of N.
If okay, maybe did I put it in the condition? Maybe I forgot to put it here. But the Poisson, it's a Poisson random variable with mean lambda. So when N is equal to Q, then lambda is equal to the sum from K equals to 1 to Q of the PKs, because the expectation.
Okay, that makes sense. Yeah.
And so you can still you can apply it basically with Q. Okay, so if there are no other questions, I'll move to the third and probably the big part of the talk, which is Changeline. So here we familiarize ourselves with coupling techniques, and we looked at the case, and we got a standard result, which is the Lecam theorem, and we gave one generalization. So for all those techniques to apply, we needed independent summations, because the main idea was to bound the total variation distance of one Bernoulli random variable and one Poisson random variable, and then to sum it up, which we could do because everything was independent. Now we are no longer requiring the B case to be independent. However, we're looking at the case where N is an integer now, not an integer valued random variable. So what is the Chen-Stein method? It's based on the following key observation. So if you have a Poisson random variable, which we call Z, if Z is a Poisson random variable with parameter lambda, then for all bounded functions on N, we have the following sort of formula on the. We know that the expectation of lambda times h of Z plus 1 is equal to the expectation of Z times h of Z. So this may come out of nowhere, but the idea is that the Poisson distribution is the only distribution to verify this identity. You can see it. You can actually show it. And here, what does this identity kind of say? It basically says that that when you add a point, it doesn't really change the distribution. It's kind of. I'm not going too much into details on that. But the main idea of the Chen-Stein method is that, well, we have this sort of magical identity on the Poisson distribution. Well, if we have another distribution that for which this expectation is close to 0, then we can imagine that we are close, that the distribution of Z is close to a Poisson distribution. Because since this identity characterizes a Poisson distribution, then if we have a distribution that almost verifies it, then you could imagine that it's almost Poisson. This is kind of the main idea of the Chen-Stein method. The main idea behind it. Oh, we can do this. Okay, not know that. Okay. Okay. So what does the result state exactly? What kind of bound do we have? The bound is the following. So we take UK and VK, random variables on the same probability space. So we couple UK and VK, and we're putting the following marginals on them. So UK, for each K, we have n of those. For each K, it has the same distribution as the initial sum. So we have n copies of the initial sum here. Okay, the UKs are just copies of the initial sum. And VK is basically each VK is basically has the same distribution as Sn, conditionally on the fact that xk, so xk, sorry, here I messed up the notation. Xk should be bks because we're looking, so okay. This is, yep, bks. The dependence between the bks is weak. So the idea is that, so you have Sn is the sum of the bks, and now you look at the conditional law that you force one of the bks to be equal to 1, and so one of the bks is equal to 1, and you look at the distribution. You look at the distribution of the conditional distribution of Sn, knowing that bk is equal to 1, and you add 1 since you know that bk is equal to 1. And if you have the degenerate case where the probability that bk is equal to 1 is equal to 0, then you state that vk is equal to 0, but that's not very important. So if we define these uk's and the vk's, so if the distance between the distance between the two is small, in the sense that if uk is equal to vk with high probability, then this means that the dependence between the xk's is weak, because the vk is basically uk conditioned on bk equal 1. So the distance between uk and vk measures the dependence between the summands, the Bernoulli random variables. So and again, if the pk values are small, then we can imagine we can get a good Poisson approximation, and this is the result. So you take a Poisson random variable with the mean sum of the pk. So you take the same mean as the initial sum as previously. You conserve the mean, and then you get the following bound on the distance in total variation between the sum and the Poisson distribution. Well, the bound is the following: you can take the minimum between 1 and 1 over lambda, and you have the sum of the pk's times the expectation of the absolute value of uk minus vk. So if uk minus vk is often 0, this expectation will be small, and the sum itself will be small. And the lambda, I did not did I define lambda? Lambda is the sum of the pk's. I'm sorry. I'll add this here. Lambda. I thought. Okay. Okay. Is the statement clear? Okay.
Yeah.
Okay. So now I'll prove this result, because once again the proof itself is interesting and can be adapted to other settings, and it will once again use coupling arguments. And I'll prove this result, and then I'll focus on examples of applications. I'll apply this to a few different standard settings. So as I mentioned, the idea is to look at the following identity, which we know that for a Poisson distribution, the identity on the left hand side is equal to 0. So we're looking at this identity for our sum of Bernoulli random variables. Okay, we can simplify it, and we can make appear. We can force UKs and VKs to appear. Okay, you just rearrange the terms, and here you can will be equal to the sum of the pk's times the expectation of basically the differences of h of uk plus 1 minus h of vk plus 1, where h is any bounded function on n. So this is true for any bounded function. So now what we have is that for any bounded function, we can rewrite h of I minus h of j as we can bound it by the difference of I minus j times the discrete derivative of h. So just the difference on two consecutive values. So we can bound our original expectation by the supremum of the discrete derivative times the sum of the pk's times the expectations of uk minus vk. And so here we've almost we see that we're very close to this. We just need to show that that the discrete derivative is the supremum is less than what I've said it before. And actually, this is something that we will do in the following way. We'll fix any subset of n, and we look at a particular function j. Okay, we look at the function j that is the solution to the following equation, which is sometimes called the Chen-Stein equation. So on 0, it's equal to 0. And then it's kind of, in some sense, it verifies the identity that was there previously. So you lambda times j of I plus 1 minus I g of I is equal to basically the indicator of is equal to 1 if I belongs to A minus the probability that the Poisson random variable belongs to A. Okay, so we just put this equation and we take a function g, which is the solution to this equation. You can show that the solution exists. You can show that the solution is bounded and that the discrete derivative, the supremum of the discrete derivative is less than the minimum of 1 and 1 over lambda. So now we have this and we have this. So this is true. This is true for any function h. So in particular, it's true for j. What happens for j? For j, we have that the probability of Sn. So if you this is the probability that Sn belongs to A minus the probability that L belongs to A. You can probability that Sn belongs to A. You can rewrite it as the expectation that the indicator of Sn belongs in A. And so we can apply this. We can apply this with the solution to the Chen-Stein equation, with I equals Sn. Okay, so we plug Sn into the Chen-Stein equation. And so now, since we have the bound for delta j, we can use this identity, which was true for any function h. We apply it with this time with for the function j, and we get the bound of the total variation distance between Sn and L. We get a total bound of the total variation distance between Sn and L, because this type of bound we have it for any a, and we have this. We have the bound that was announced. So what we did was we took a particular bounded function, which was the solution to the Chen-Stein equation here, and we sort of used its form to plug in to make this total variation distance between Sn and L appear. Okay, I hope this is clear. So so to give a summary Chen-Stein method, because now we've proven it, but we haven't really seen how it works in a concrete setting. So this is what I'll do from now on. So what we did, we wrote the total, basically we wrote the total variation distance as a mathematical expectation for a certain function g. We bounded both the function g and the discrete derivative. So this part was skipped in the proof because it's just technical calculation. It's not very interesting. It's just a study of the Chen-Stein equation. And then the most important part is you use a clever the of the absolute value of the difference between UK and VK, we want to make it small. So UK and VK each need to satisfy, we have a constraint on the laws, and so we have a constraint on the marginals. And in the same kind of idea as in the case of Le Cam, we want to construct a coupling of UK and VK such that the expectation of the absolute value of the difference is small. So basically, we want to construct UK and VK in such a way that so as to make them coincide as much as possible, just as before. And so, so this kind of idea makes it the natural question is to sort of compare it to the Le Cam setting. So if you suppose the BKs are independent, so we're now in the case where we had the Le Cam theorem. So what does the Chen-Stein result give us in this particular case of independent summands? Well, now you just take UK. It will all depend on the coupling we take of our choice of UKs and VKs. But here, a simple choice of UK equals to Sn for all k between 1 and n, and VK equals to the sum of the BK prime. So we just take all of the BKs different from k. Then you can compute the expectation of the difference of the absolute value, because the absolute value is just the difference is just BK by construction, and the expectation of that is just PK. And so, and the minimum of 1 and 1 over lambda is less than 1 over lambda. So you get the following get the following result. So you sort of you can get back and something better. Because you get instead minimum of 1 and 1 over lambda. If we put that directly, this is minimum of 1 over lambda and 1 times the sum of the pk squared. So we got this part this is what we got that was better than the Le Cam original result here. So this Chen-Stein method is more general in some sense than the Le Cam theorem, because we can get a better bound than Le Cam for the Le Cam setting. Okay, so now I'll give an important example, which is classical example of application of the Chen-Stein method, is when the variables are negatively related. So they're not independent, but we put another condition on them. Basically, we take copies of the random variables, and we want them to be, those copies to be constructed in such a way such that I'll get the pen back. Okay, such that the copies of the second sample we take, so we basically take 2 samples constructed in a particular way, which will be clear here. But the negative relation part comes from this condition. Basically, construct them that the elements of the second is smaller than the elements of the first sample. This is what we call them negatively related. And so what are the conditions on the samples? So the elements of the first sample are just have the vector has the same law as the initial vector of the Bernoulli of the random variables, sorry, not of the initial random variables, and the second sample has the same law as the conditional law of the sample, conditioned on BL equals 1, and we take L for we take that over all values of L between 1 and n. Okay, so when we say that our random variables B1 Bn verify this condition of being negatively related if we can construct for each L the following samples that verify this, basically. So the first sample is just initial random variables, and the second sample follows the law of the initial random variables, and the second sample follows the conditional law conditioned on some of one of the elements here being equal to 1. And you do that for all possible values of that, basically. And so when the random variables are negatively related, we have the following result. We have we can give a of U minus V way. So we can bound the total variation distance between Sn and L by the following elements, which only depend. Now they only depend on Sn, because lambda is basically the expectation of Sn, and the variance of Sn can usually, in many situations, can be computed as well. And so
I cannot hear Michel anymore. Am I the only one?
Oui, c'est pareil.
Okay, I will check directly on his office. Okay, still nothing. I will ask him to reboot his tablet. Sorry for the interruption. Perfect.
Okay. I think this works now.
Yeah.
Okay.
C'est bon.
Okay. So, sorry for this interruption. Sorry. So, which part? Where was I when the connection stopped? Can you hear me now?
Yes, we can.
Okay. Was there an interruption at some point?
I believe it was, yes, around there, more or less one slide.
Okay. Did you get the definition of negatively related random variables, or was there?
Yes.
You stop there. Yes, it was
okay.
interrupted.
Okay, so we take B1, B1, Bn, which are negatively related random variables. Now, why is this property interesting is that in this case we can have an explicit bound of the total variation distance, which does not, which is now explicit and only depends on Sn. It can often be computed explicitly in many applications. And so here we can construct UK and UL and DL that will satisfy the condition that is needed from step 3 here. So the condition on the coupling, basically, to make the expectation small, and UL minus VL are negatively related. And so because of that, we can compute the expectation. We can remove because of the property of negative relation, we can remove the absolute value and compute explicitly the expectation, and you get at the end you get exactly lambda minus the variance of Sn. So in the negative related case, you can replace the sum of pk's times the expectations of uk minus vk for some uk vk by an explicit bound which only depends on Sn. So this is very useful in applications, and this I'll present a classical application right here to approximate by to give a Poisson approximation of the hypergeometrical distribution. Sorry. So what is the hypergeometrical distribution? It's just the following. You consider n boxes, and each box has has the place for one ball only in each of the boxes. And you take m balls, and you distribute m balls amongst the n boxes uniformly, which means that each of the configurations has the same probability. And then we introduce the variables bk. Bk is equal to 1 if there is a ball in box k, and 0 otherwise. And we call Sn. Sn will be the sum of the bk's. And Sn, we say that Sn little with little n is which is less than or equal to big N, which is big N is the number of boxes. And we say that Sn has a hypergeometrical distribution. And we call P the ratio little m over big N. And so, of course, this ratio is strictly less than 1. Since we ask m to be less than big N. And so the first result is that in this setting, so if you take a hypergeometrical distribution Sn, you look at it is the sum of the bk's, and the bk's are negatively related. And so to do that, you have to define for any L good samples of the Bernoulli random variables that will be you can show that they are they verify the 3 properties required for them to be negatively related. So the second sample is the conditional sample based on the fact that we have a ball somewhere. So we do exactly that. We place a ball in box L, and we distribute uniformly the other balls among the other boxes. then B prime LK is equal to 1 if there's a box in ball in box K and 0 otherwise. And then you have by construction that the sample there is the conditional law of the original sample conditioned on there being a ball in box little l. Now, to construct the other sample, we toss a coin with heads probability P. So the P is remind you, the ratio of basically the ratio of the filled boxes. And if we obtain heads, then we take our first sample to be equal to the other sample. And if it's tails, then what we do is we take the ball that was assigned to L by the first sample, and we uniformly choose another empty box and set the ball that was assigned to L there. And then we set the sample to be equal to the law of the B1 Bn, because now we don't know anymore where the ball is. So there's no conditional distribution anymore. And you can check that when you write this way, the third condition here, we will have B prime LK, which will be always less than or equal to B LK. Simply by construction here. And so now let us apply the Chen-Stein method to the hypergeometrical case, and we see that we will have a very explicit, very simple bound of the total variation distance, which will only depend on little n, little m, and big N, so it's completely explicit. And the Poisson random variable has a parameter where once again we conserve the mean. Has the same mean as the N. And since they're negatively related, we can apply the result from a previous section. We multiplied by lambda to make some things easier later on, and we have that the total variation distance is equal to the less than or equal to the minimum of 1 lambda times 1 minus the variance of Sn divided by. So for the hypergeometrical distribution, this variance can be explicitly computed. So we're going to be equal to n times p times 1 minus p times big N minus n divided by big N minus 1. Okay. So now we can plug that in here in the previous line and just obtain the result. So as you can see, the proof is pretty simple, and we get a nice explicit bound for the total variation distance between the hypergeometrical distribution and the Poisson distribution. And so we sort of have seen the power of the Chen-Stein method for a number of various settings already, and so these are just a few of the generalizations that are possible. So as I mentioned, you could imagine you have compound Poisson limits. So you have when the summands are no longer just Bernoulli and the Bernoulli and the variables, you can have non-Bernoulli. So this is related to the fact you can have non-Bernoulli summands. You can generalize it now. We work specifically with random variables. There are also many results for when the objects of interest are stochastic processes, or typically approximations to a Poisson point process. And we just wanted to mention that the Chen-Stein method is kind of a derivation of something called the Stein method. Chen, who was Stein's PhD student, derived it for Poisson. But the Chen-Stein method is used to obtain Gaussian approximations in the continuous set. So basically, you also have a functional identity that is verified by only the Gaussian distribution. You have the same idea of you have your distribution is approximately Gaussian if the functional identity is more or less approximately verified. So the idea can be also generalized to other distributions. And so to finish, I just wanted to mention a few elements of bibliography for those who are interested in the subject. So most of what I presented today can be found in Lindvall's very, very, very nice book, Lectures on the Coupling Method, which I very much recommend. So the results on on the generalization of Lecam that I presented today, to the best of my knowledge, is not found anywhere yet. But so if you're interested in other generalizations of Lecam's initial theorem, there are many of those present in the Lecam's book, Asymptotic Methods in Statistical Decision Theory. In particular, if you're interested in compound Poisson limits, you can find that there. He for some reason, he calls the total variation distance the L1 distance, which is not very usual, but okay, anyway. And if you're interested in the best review of the Chen-Stein method that I found was a book by Barbour, Host, and Janssen, which is simply called Poisson Approximation, but it has a lot of information about the Chen-Stein method in there. So we come to the end of my talk, and if you have any questions, I'll be glad to answer them.
Thank you, Michel.
Thank you, Michel.
Yeah.
Actually, I have a question, but I guess
Yeah.
it's not perfectly related to your analysis. My question is, in your second section, you say a random variable n, a sum of Bernoulli distribution. Do you think you can derive the probability density function by random variable algebra? Say there are two random variables. One is Bernoulli random variable, another is n. Then you apply the multiplication. So the Sn here should be a random variable n times a random variable b. Do you think it works to derive the PDF?
So you have the Val identity to define to derive the expectation, but I don't think you can derive the PDF explicitly, because even in the case where n is Poisson, in the case where n is Poisson, here what you get is a compound Poisson random variable. If the BKs are if the BKs are IID. So even in that case, there's no you can get an explicit form for maybe the characteristic function and the MGF, but I'm not completely convinced.
That's my understanding. Do you think it works by change this sum into a multiplication explicitly?
Yeah. If you look at that when you want to look at it as a convolution of laws.
Yes, that's true.
Yeah. So that's actually the method used to prove. Because of maybe. Well, so what do you want to do? You want to reprove the same result using characteristic functions, or do you more want to compute to just see if you can compute the PDF?
I just want to compute the PDF, but I guess I'm just out of curiosity, because when I look at this n is a random variable, it occurred to me that it might be a random variable multiplication. Yeah, this is out of my curiosity.
Yeah.
So thank you for the answer.
No problem.
Yeah. So one comment is about the this adding one point and not affecting the law. This is Slivniak's theorem, actually, or a special case of it, and it's beautiful. So we know that in the Poisson point process case, even in higher dimension, Slivniak, the palm being just the Dirac measure at 0 plus the Poisson point process, is a characterization of the Poisson. And here It is fantastic that the same principle is used to compute the distance, the variation distance to Poisson law, and it's quite amazing that this is the same principle, Slivniak and Chen-Stein.
Yeah, I agree. I didn't mention it because I didn't want to go to processes. I thought it was maybe too bit far from the lecture, but yeah, it's very beautiful that you can see the parallel between something on a theorem on palm theory and then this distance in total variation to it's not completely clear how they're related at first glance. And this they have the same underlying principle of what happens if you add one point. And you look at what happens. Yeah, thank you for the observation.
Thanks again.
To elaborate on what Godon was saying, so if you go to analytic method based on transforms, on characteristic functions, things like that, you have something way weaker. So the beauty of this is to use the total variation. Whereas if you go to the law, and then try to do manipulation on the law, this will be, this will tell you things on weak convergence, but not on variation, right? So I think the fantastic difference and novelty compared to analytic methods which were used in the past is this use of variation distance. This is the essence of it.
Oh, thanks, Professor.
Thanks again. So I will stop